Welcome to this new video. In this video, we're going to review some of the concepts of hydrologic cycle, and we're also going to introduce the radiation equation. Let's start with problem 1.12. It says, imagine a parking lot in Chicago that acts like a giant shallow bathtub. This parking lot is 6.7 acres big, which is a lot of space. It rained on the parking lot, and we measured the average amount of leftover water flowing out, the runoff, over a 2-hour period. This runoff was measured at a rate of 20 cubic feet per second. Here's the tricky part. Not all the rain that fell soaked into the ground or flowed out as runoff. Some of the rainwater collected in puddles on the surface of the parking lot. This water that forms puddles is called depression storage. For some reason, we know the depression storage depth, and this is typically 0.08 inches. We want to find out the total amount of rain that fell based on the following information. We have runoff rate is 20 cubic feet per second for 2 hours, and the depression storage is 0.08 inches. We're going to solve this. We're going to use the hydrologic cycle equation, which is this one here. And we're going to have the values for each part of the equation. To solve we're being asked for the precipitation, right? Find the amount of total rainfall. So it's going to be the precipitation. So solving, we are given the area is 6.7 acres, initial extraction 0.08 inches, runoff 20 cubic feet per second. Now, during precipitation, during the 2 hours of precipitation, we can assume that all of these three values are negligible. Evaporation, transpiration, and infiltration is also negligible because we're talking about a parking lot. It has an impervious surface, so the water that infiltrates is pretty small, so we can not take that value into account. Okay, so now we need to get these values to match. We want to express precipitation in inches, so it would be smart if we start changing all these values into inches, right? So let's start for the area. If we have 6.7 acres, in 1 acre, we have 43,560 square feet. We cancel acres, we can multiply 6.7 times 43,560, and this will be the area in square feet. now, now that we have that initial expression in inches, let's convert this into cubic feet, the runoff. We have it as a runoff rate. We want the runoff volume, right? So this is for 2 hours. The conversion would look like this. It will be 20 cubic feet per second. There are 3,600 seconds in 1 hour, and the storm lasted 2 hours. So seconds cancel, hours cancel, and we're gonna be left with cubic feet, which will be the volume runoff. It will be equal to 20 times 3,600 times 2. And this is cubic feet. Now, here the runoff equals precipitation minus initial extraction. We're interested in precipitation, so it's going to be precipitation equals to runoff plus initial extraction. We have runoff as cubic feet. We can convert it into feet if we divide it by the area. So we do this equals the runoff cubic feet divided by the area, square feet. This will be the value in feet. And to match it with the initial extraction units, 2 inches, we need to convert this value to inches. So if we have 0.49 feet multiplied, there's in 1 foot, there are 12 inches. Feet cancel, so we need to multiply it by 12. So this is the runoff volume in inches. So all we need to do now is plug the values in there. It's gonna be the runoff in inches plus the initial extraction in inches. So it's about 6 inches. And that's the answer for this first problem. Now the next problem, it's a little bit more complicated, and I feel I generated an image that I hope it helps explain what the context of the problem is. 1.13, Imagine a 24-acre watershed area that feeds rain into a stormwater pond. Let's say the area is everything that the peaks of these mountains contain, and this will be the pond. So everything that melts from up here or precipitates on this area is gonna run off to this pond. And let's So we have a 24-acre watershed area in the rain that feeds rain into a stormwater pond. Rain falls for 2 hours at an average rate of 1 inch per hour. Not all the rain becomes runoff though. A runoff coefficient of 0.5 tells us only half of the rain actually contributes to runoff. The pond itself is 2 acres on average and has 5 feet of water at the start. So let's say this area is 2 acres and the depth of this water here is 5 feet. Um, where we 5 feet of water at the start. There's also an interesting aspect. The pond loses water through its sides at a rate of 4 inches per hour when the water level is above 5 feet. Through the pond side walls area of 2,100 square feet. We want to find the depth of the water in the pond above the 5 foot level 8.2 hours after the rain stops completely. To solve this, we need to consider the amount of rain that becomes runoff, the size of the pond, and the water lost through the sides of the pond. Okay, so we got 24-acre watershed area, and we are given the precipitation in a rate. So let's convert this precipitation into a volume. So we have 1 inch per hour for 2 hours. Hours cancel, we're gonna get 2 inches, right? So that's gonna be 2 inches of total precipitation. Now, but we say that the runoff is equal to 0.5 the precipitation. So it's gonna be half of it. Runoff is gonna be equal to 1 inch only. And we can consider negligible the evaporation and transpiration again. And we are given that the infiltration is 4 inches per hour for 8.2 hours. So let's say we have this in inches. Let's convert this to inches to feet so we can give a final answer in feet instead of inches. Since we are using feet here for the depth of the given depth of the water in the pond. So this is going to be 2 inches, there are 12 inches in 1 foot. So it's going to be equals to 2 divided by 12. Okay, so this is the precipitation in feet. Now we want to find the infiltration also in feet. To do that, we got 4 inches per hour times 8.2 hours. So that was going to cancel the hours. Now there are 12 inches in 1 foot. So that's going to cancel the inches and going to leave us with feet. And if we want it in cubic feet, we need to multiply by the area, which we're giving it's the area of the walls of the pond are 2,100 square feet. And that's going to give us the volume of infiltration in cubic feet. So this is going to be equal to 4 times 8.2 times 2,100 divided by 12. And that should be cubic feet infiltration. Let me double check with my notes. 5740. Yep. Okay. So now that we have this in feet, let's convert this runoff into also cubic feet to have all the units the same. So that's going to be 1 inch times the area. The area of It's 24 acres. How many feet are in acres? 43,560. So acres cancel. We need to convert inches to feet, 12 inches. So these inches cancel. 12 inches in 1 feet. This is gonna give us a value of cubic feet. And that's gonna be the runoff. So that's gonna be equals to, well, 1 times 24 acres, which is the area, times 43,560, all of that divided by 12. And this is cubic feet. So we got, yep, that's the same as my notes. Now, let's see what we have done so far. Of all the water that precipitated, only half of it actually runs off into the pond. So that runoff, which is the total precipitation is 2 inches, but only 1 inch runs off into the pond. And this 1 inch represents 87,120 cubic feet of water, uh, because it's 1 inch all over the 24 acres. And we have made the conversion, it's 87,120 cubic feet per cubic feet. Now, once that amount of volume of water gets into the pond, in 8.2 hours after the precipitation, 5,740 cubic feet infiltrate, they exit out of the pond. So the volume of water that stays there after 8.2 hours will be all the water that came in minus the water that exited through infiltration. So let's say here equals all the volume of water runoff that came into the pond minus the water that infiltrated, that exited the pond. So this is the volume after 8.2 hours. Cubic feet. Okay. Okay. So this is the volume after that. Now, we are given the initial volume is 5 feet. If we want to know what's the height of all this volume only, we need to divide it by the area, right? So we have to do the total volume divided by the area. We haven't converted the area into cubic feet, but we can do that. So 2 acres of the pond, in 1 acre, we have 43,560 square feet, and we're gonna get square feet. So this is gonna be equals to 2, sorry, here, equals to 2 acres times 43,560. And that's the same area of the pond in square feet. So the height is gonna be equals to the volume divided by the area. And this is the height in feet. So if the initial height was 5 feet, now the height will be the final height after those 8.2 hours is gonna be 5 plus this. And this is our answer. Sorry, I hope this made sense and was somehow easy to understand. Now let's go to the last problem of this section, which is gonna be about solar radiation. And let's get started. I have some notes for this problem just to understand some of the units and some of the concepts that the problem is stating. So hopefully that helps to understand. It says the first part, we have 1, 2, 3 parts on this problem. The first part says the solar radiation at the outer atmosphere, solar constant, is approximately 2 calories per minute square centimeter. Note 1. The meaning of this unit, calories per minute centimeter square, tells us the amount of energy in calories that passes through a 1 square centimeter area each minute. In this context, it describes the rate at which solar radiation hits the Earth's outer atmosphere. This expression tells us that every minute, 2 calories of solar radiation pass through that tiny square. So this is what this unit means. Since the projected area of a sphere, the Earth, is 1/4 the surface area, the incident outer atmosphere's solar constant is 1/4 times 2, or about zero point 0.5 calories per minute centimeter squared. What is the approximate solar radiation incident, absorbed radiation, at the Earth's surface in calories per minute square centimeter? So if that's the solar radiation that hits outside of the Earth, it's asking us what's the solar radiation at the surface of the Earth, like where we live. And according to this graph, is 51% of it. So to solve that part A, it would be 0.51, 51% times 0.5 calories per minute square centimeter. So this will be the answer of that first question. Calories per minute square centimeter. Now, let me double check that. Yeah, that's correct. Now, part B, this is what the Earth's surface, the ground, absorbs. Now, part B is asking us if the Earth radiates back at an average Earth temperature of 15 degrees Celsius, what is the approximate Earth radiation in calories per minute square centimeter? Assume the Earth is a black body with an emissivity of 1.0. Okay, so we need to use for this the radiation equation to find out what's the radiation that the Earth emits back. Um, so this is the equation: radiation equals sigma times epsilon times T, that represents temperature to the fourth. And sigma in this case is a constant, and this is the value 5.67 times 10 to the negative 8 watts per square meter times degrees Kelvin. Emissivity doesn't have units, and temperature needs to be in degrees Kelvin. So we are given that since we are assuming the Earth as a black body, so that's going to be 1.0 of emissivity. And then we are given the temperature in degrees Celsius. So 15 degrees Celsius would be 288.15 Kelvin. And now we just need to plug those values in, and we should be getting the radiation. That's going to be equals 5.67 times 10 to the negative 8 times 1, which is the emissivity, times the temperature to the fourth. We get 390 times 0.89. And let me double check. Oh, okay. So that's gonna be, we need the units. That's going to be watts. So if we do that here, so we can all understand radiation equals sigma times 7.4, 5.67, 10 to the negative 8 watts per square meter Kelvin, 1.0. Temperature is 288.15 degrees Kelvin, to the fourth. So we found the value that is 390.89, and that's going to be watts over square meter. And then this Kelvin to the fourth and Kelvin to the fourth, they cancel. So we have watts over a square meter, which is equal. We know that we have a conversion table here. 1 watt equals 14.33. So 1 watt equals 14.33 calories per minute. So this cancel and we get equals this number times 14.33, and we get Okay, and now we need to convert in 1 meter, there are 100 centimeters. So in 1 meter square, so we need to divide by 100 square. So two more zeros, and we get 0.56. And these meter squares cancel with these meter squares, and we get the value of 0.56 calories per minute centimeter square. Okay. Uh, this is the answer for part B. This is how much energy is emitted back from the Earth's surface. Now, the C is asking us which is larger, so we can see that the emitted radiation is larger, right? So we can, this is the answer, and it's by how many times? So we can divide and get a, the answer is just 1 divided by this value is, and is greater by about 2.2, 2.2 times. So this is the next answer. And the question is, why aren't we freezing to death then? Um, because obviously, according to these equations, we are sending more energy out or more radiation out than the radiation that the Earth is receiving, right? So eventually, since we're losing more radiation than the radiation that we receive, we should be like freezing, right? Getting cold. And the answer actually is due to the greenhouse effect. And I have a statement here in my notes that says the greenhouse gases in the atmosphere, such as water vapor and carbon dioxide, absorb most of the Earth's emitted long-wave infrared radiation. This hits the lower atmosphere, which in turn emits long-wave radiation, some of which radiates back towards the Earth's surface, keeping our planet warm. So it is thanks to the water vapor and uh, carbon dioxide. So all these gases keep kind of trap all this heat that the Earth is emitting back. So in some way, even though we keep trying to get rid of this greenhouse effect, it's actually keeping us all alive. So that would be the answer for this part E. Now let's move on to, yeah, we have covered this. I didn't read it. We already have covered all of this. You can read it on your own if you want. Okay, for the second part, we are given calculate the total long wave radiation energy in kilowatt hours from 100,000 acre, 70-degree Fahrenheit Utah Lake with emissivity of 0.97 on July 4th. If our energy costs about 10 cents per kilowatt hour, how much in dollars is the energy radiated from Utah Lake worth on July 4th? So we're gonna have to compare our radiation value to kilowatt hours. So we have it here in watts. So let's convert this sigma value into kilowatts, which would be sigma equals 5.67 times 10 to the negative 8 watts per square meter to the fourth. So there are in 1 kilowatt, there are 1,000 watts, right? So watts cancel. So if we divide, this should be 5.67 times 10 to the negative 11, right? And this will be kilowatt per meter square degrees Kelvin to the fourth. So let's change this, divided negative 11, and this will be kilowatts, right? Let's expand this. Okay. Now we got the value of emissivity 0.97, and this will be, they're giving us 70-degree Fahrenheit to Kelvin will be 294 to 61. Yep, 70. Yep, that's what it will be. Now we need to solve for the radiation. Now, given that we have, let's do this. So we have the radiation equals 5.67 times 10 to the negative 11 kilowatt per meter square degrees Kelvin to the fourth. Now the emissivity is 0.97, and then temperature is 294.261 degrees Kelvin to the fourth. We are gonna get equals this value. I don't know if you grab it. Let's see. Times 0.97 times this to the fourth. Yeah, it won't work. Let's do this by 5.67 times 10 to the negative 11. Let's see now. Okay, so we got 0.4124, 0.4124, and that will be this Kelvin cancel kilowatt per square meter. Let me double check that. Yep. So that's the radiation that we get, but we're given an area now. So we're given that the area is 100,000 acres. Now, in 1 acre, there are 4,046.86 square meters. So acres cancel, and then square meters cancel, and we get radiation only on kilowatts. So that's gonna be this value multiplied, let's keep adding up here, multiplied by 100,000, 1, 2, 1, 2, 3, times 46.86. And that's our value in kilowatts. Now, it's a very large value. Now, in the whole day, so we need to multiply that 24 hours in 1 day, and it lasts all day. So let's multiply that by 24. And that's the wrong one, this one, by 24. And that will be our value for kilowatt hours, right? So it's about kilowatts hour. Now, we want to know, okay, let's do commas. So this is about, yeah, this is a large value. It will be 4 times 369, 10 to the 9 kilowatt hour. And now we want to compare it with the money. We'll have to multiply this value times 0.10 per kilowatt hour. Kilowatt hours cancel. And now this is equal to this times 0.1. And this is in dollars, right? Uh, so it's about 368. This is about equals 4 times 10 to the 8 dollars. And that's the answer for this second part. Just need to be very careful with the conversions, but if you do it right and take your time, you'll get there. Now, radiation equation, we're going to use that again for the third part. It says find the temperature in degrees Fahrenheit of a 5-acre Dallas parking lot if the radiometer measure 1.6 times 10 to the 8th calories per minute radiation from the parking lot. Okay, same idea, except that now we need to use the same equation to solve now for the temperature. So solving for the temperature, it will be the radiation over sigma times epsilon elevated to the 1/4, or the fourth root of this value, right? So the emissivity, we can assume that it's going to be 1, yeah, because it's a dark surface, it's a parking lot. So 1.0. So for this part, we have the normal constant value of sigma, but we're gonna adapt it to our problem since we're given an area. In our case, will be sigma equals 5.67 times 10 to the negative 8 watts per square meter degrees Kelvin to the fourth. And we're gonna multiply by the area, 5 acres. And we know that in 1 acre, there is 46.86 square meter. So acres cancel, square meters cancel, and we're gonna get this is equal to 5.67 times 10 to the negative 8. All of that times 5 times 40, 46.86. And this is our new value. And it will be watts per square degrees Kelvin to the fourth. Now the emissivity is 1, radiation we're given this value, calories per minute. Now we need to use the radiation equation. So this is going to be D is equal to radiation over 1.6 times 10 times 10 to the 8th 0.001147 watts given to the fourth times. There is in 1 watt 14.33 calories per minute, and then all of that times 1, which is the emissivity. So this part is sigma, and we are canceling the watts. This is going to be t to the fourth equals 1.6 times 10 to the 8 degrees Kelvin to the fourth. 0.001147 times 14.33. So that's gonna be, let's do, this is the to the fourth. This is going to be equals to 1.6 times 10 to the 8 divided by this value multiplied by 14.33. Now D will be equal to this value elevated to the 1/4. So it's about 314 degrees Kelvin. So that to Fahrenheit will be, let's do Kelvin to Fahrenheit, and it was 314. So it's about 105.5 degrees Fahrenheit. And that should be the answer for this problem. So sorry for the confusion in all the conversions, but we go to the right answers. So hopefully you find this helpful. And if you have any questions, just let me know. So in this video, we have covered, we have reviewed some of the concepts of the hydrologic cycle. And we have also covered a new concept of radiation using the radiation equation. So good luck working out these problems. See you in the next video.